Can I start? Thank you. So in this talk, together with Rustan, Leino, and my team of students, Ștefan and Roxana should be somewhere here in the room, we are proposing to add an interactive proof mode to the Dafny system, and the talk is about how we can do that. I'll structure the talk as follows. After a very brief introduction, I'll show you a running example of how a proof mode could be useful, and then I will demonstrate the proof mode that we propose from the user's perspective and briefly explain how it works behind the scenes afterwards. Okay, this audience likely does not need an introduction to Dafny, but just to make sure we are on the same page here. Dafny code looks typically like this. So each method has a specification with preconditions and post-conditions, and then the code is typically annotated using some helper annotations, in this case some invariants. And the system, at compile time, it verifies that the method meets the specification. And simplifying somewhat and skipping a ton of details, the way it works is that it gets translated into an intermediate language, into Boogie, which itself then translates the invariants, the specifications, into first-order formulae that are sent to an SMT solver, typically Z3. And you have here an example of what a verification condition might look like for the first invariant there. OK. This is all very nice when the code does verify. But when the code does not verify, things are less nice, because typically you have no idea where the bug is. Could be a bug in the code, in the specification, or in the helper annotations. And experienced users of the Dafny system, they work around this by building up some sort of mental model of what will the prover be able to prove, and then they will iterate in a code specify prove loop until they are happy with the result. Okay, and I'll show you an example of how to develop a proof in Dafny for this lemma here, for this trivial lemma here, which does not verify automatically because it has some sort of nonlinear arithmetic in it. So it states that x times x plus 1 is divisible by 2. The system fails to prove it automatically, so an experienced user will typically start with a placeholder proof. So say assume false, so anything follows. And then later on, when it comes time to make the actual proof, you start iteratively working on it. So the first thing you might check is, well, does Dafny know that the modulo operation distributes over multiplication? You try this assertion here, you run the compilation again, and this assertion fails. So this doesn't work, you need another strategy. So the other strategy, you could try a case distinction. You could think about, wait, what happens if x is even or odd? And then fill in each of the cases separately. I'm sorry about this, but the pointer is not working properly. So, and then you can say, well, I'm working on the first case here. Does the prover know that x is 2 times x divided by 2? Yes, this does work. OK, and then you say, well, I'm going to help it now. I'm going to tell it that x times x plus 1 is 2 times something. OK, with these helper assertions, the first case goes through, and then the second case is analogous. So give or take, in roughly 6 steps, you end up with a proof of this lemma. But this development strategy has a number of issues. It is time consuming because you typically need to recompile with each try. And you use the prover as a black box. You never really know what it can do or it cannot do. And also, the verification condition is not explicitly visible. So you sort of have to look throughout the code. What are the things that the prover knows? What does it need to figure out at this point? This is in contrast with interactive theorem provers like ROC or Lein. In ROC or Lein, you typically have the proof context at all times visible on the screen. So you have some hypotheses and the goal that you should prove. And then you guide the prover using tactics until you finish the proof. But the thing is that you receive immediate feedback. So you don't need to recompile the entire development. Of course, there are a number of disadvantages to interactive theorem provers that I won't go through. What we propose is to combine the two approaches by adding an interactive proof mode to Dafny'. Now I'll show you how the proof mode that we propose works from the perspective of the user. When the user has a verification condition that fails to discharge automatically, such as the one that I've shown earlier, we want the user to annotate it using the IPM annotation for interactive proof mode. And then we start our proof mode, which is a Dafny' script. When the proof mode starts, it presents us with what is known, the hypothesis, currently nothing, and what is the goal that we should meet. And it expects us to enter a tactic that helps create the proof. Okay? And one of the first tactics that we have is a tactic called check, which simply states, does Z3 know this fact, which is that the modulo 2 operation is distributive over multiplication. And when we enter this tactic into the proof mode, immediately, without recompiling everything, tells us that no, the prover cannot not prove this thing, so we need some other way around this. Okay? So the other tactic that we have is a tactic for case analysis. It is called case. So I'm saying do two cases, one where x is even, the other where x is odd. Okay? What happens here is that the proof goal is replaced by two goals. In the current goal, x is known to be even, and in the second goal, it will be the other case. Okay? And still, we need tactics to discharge the current goal. Okay? The most important tactic that we have is the assertion tactic. So this works like assert in Dafny'. What it does is it has this intermediate assertion that it proves from the current hypothesis, and then it adds the intermediate assertion as a hypothesis and brings back the original goal here. Okay? And finally, after all goals are discharged using tactics, what is interesting is that the interactive proof mode outputs Dafny' code that can be copied back into the lemma. And the lemma, the Dafny' code proves that lemma there. Okay. Currently, we support a limited number of tactics and commands, but we hope to increase this. Okay. Now I will explain a little bit how the proof mode works behind the scenes. And I have told you that in Dafny', typically the problematic verification condition is not explicitly visible. It's sort of, you can sort of recreate it if you look at the line that is failing the verification, but you can have some invariants that are known, some preconditions, and so on and so forth. This is not exactly true, because you can have Dafny' output the smtlib file, so the verification condition that goes to the Z3 solver, by having it create the boogie file, and then from boogie you can generate the smtlib file using these two commands. And then the verification condition is visible, but it's not readable. So this is the verification condition that we see in smtlib for the lemma that I used as a running example. And you can see that it is polluted by this control flow construct, which is simply used for reporting back some errors, and by boogie. And then here there are a bunch of annotations about the heap, which are not relevant to the current verification condition because there is no heap. And then finally, the core of the verification condition is here. But still, it is not terribly readable because the arithmetic operations are not the SMT-lib arithmetic operations. They are functions, mod and mul, axiomatized to behave like the arithmetic operations. And then the variable name x is mangled. It is now x sharp something. And finally, the constants from the Dafny code are boxed using this lit-int thing. Okay, and the way the proof mode works is that it reads this SMT-lib file and it translates back what we have here into Dafny speak. In order to do this, we have to use, we slightly augment the Dafny compiler. We have it create programmatically a number of helper functions that we call underscore protect something, which will help do the back translation process. So the protection functions, they work as follows. So when our version of Dafny reads up this lemma, it will protect every identifier with the right string, and this helps us unmangle the names. Okay, there is this protect to prove annotation, which helps us identify which verification conditions should go to the interactive proof mode and which should not go there. And finally, this protect scope thing helps us with name shadowing. And the verification condition is now even worse for a human being to understand, but all the information is there for the computer to extract back the Dafny code using Dafny speak. So the architecture of the system is here. In the initial Dafny code where there is an issue, the user should annotate the problematic verification condition with IPM. We run the instrumented version of Dafny, which adds the protection functions. We generate the boogie code. From boogie, we use stock boogie to generate the SMT-lib file, which we parse, and we back translate it into Dafny speak. The user interacts with the proof mode, and during the interaction process, we do not call Dafny again and again. So there is just one call to the compilation pipeline, which is here. And finally, the proof is output. You can take a look at the proof mode. It's on GitHub. The goal is to support, in a faithful way, a large subset of Dafny. Okay. For the current prototypes, we take some shortcuts. So we support a very restricted subset of Dafny, which is ever increasing. And we have a bunch of hacks, like the way we parse SMT-lib or the Dafny expressions. And we also have a limited set of tactics and meta commands. But in future work, we plan on expanding this, so to handle a significant subset of the Dafny language, but in a faithful way. So what the proof mode can prove should be exactly what Dafny should prove. And I should say that the difficulty here is that Dafny is very monolithic. So it always starts with the entire code, the entire Dafny development, and generates all verification conditions, sends them to the SMT solver. So there is no incrementality in the Dafny compiler. So this makes adding a proof mode difficult. And we want not to run Dafny with every single command. We want our proof mode to be very fast. Okay. Obviously, the back translation process is, empirical, so we should empirically validate it on a number of examples, and we plan on adding some more tactics. And finally, of course, in the future, we want to integrate with some other tools like the Dafny counterexample generator or the Z3 axiom profiler. And ideally, the proof mode could be integrated into VS Code. You just could click and create the proof directly in the IDE. I think I am done with what I wanted to tell you. I'm happy to answer any questions.
Hello. Do you have an idea how to support rewrites? I don't see you have rewrites. What do you mean by rewrites? You can rewrite a sub-expression by like associativity when you're pushing.
You mean like a tactic?
Yes.
Yes, so we could add a tactic for rewrites. So currently we could support rewrites by doing assertions, but in the future it would be one of the tactics that we would like to support. We also plan on supporting calculational proofs as well.
Hello, thanks for the talk. It was very nice and very interesting. You have spoken about translating back from the VC level to Dafny level to print the VCs, but do you need another translator to translate whatever you put, for example, in an assert tactic to the level of the VC, or can you use Dafny directly for that?
So our current prototype uses a hack for this. So we parse it as a Python expression essentially, and we translate it recursively by hand into Z3. And we do this for a limited set of operations, so arithmetic and whatnot. But we plan on supporting a large subset of Dafny, a large subset of the Dafny expression language, but without calling Dafny at every step. So we have a number of ideas of how we could do this faithfully by using the Dafny parser, but in a very fast way.
So this, without calling the Dafny at every step, I didn't quite understand how it works. Is that like if I, as a user, I introduce a new like assertion or a case, or like I want to use this tactic, I do introduce like some new Dafny code or something like, right? So how can you actually support that without integrating it into?
Construct in the proof mode. So for example, for the case tactic, we directly split the current verification condition into two verification conditions. For the case tactic, it's very simple. We add the first case implies the initial verification condition, second case implies second verification condition.
So you added directly to the end, like to the compile?
Directly at the condition level. We work directly there in the proof mode.
Let's thank the speaker, and that ends our first session.